Hello again, it's the GD&T Guy. Just for starters today, thank you so much to all of you who have liked the videos and who have subscribed to the channel. It means a lot to me because I know these videos are long, usually much longer than I want them to be, or what I think a normal person's attention span is. They don't always look great. I don't always look great. I always catch little things in editing that I realize were not quite right, or maybe not the best way to say something. But you keep watching them, and they're doing better with time, which tells me that there's an audience for this content, whatever it is that makes it special. And another really great thing has been the comments. I have really been enjoying the comments, mostly because they've been overwhelmingly positive, but also that they reflect that you've been paying attention and that I'm doing something right in choosing topics. You know, not everybody likes or has time for a big, in-depth conversation about GD&T like I do. And so I was happy to receive this comment from an E. Sperling on episode 6 of my series on dowel pins as locating features. The comment is well stated, and it actually gives me an opportunity to maybe correct or revise one or two things about those videos that have been nagging me. I know. You're probably wondering how I earned the title GD&T Guy if I'm out here making videos with mistakes in them. So we'll get into all of that. But let's have a look at this comment, maybe paragraph by paragraph. It starts off, in this video, you dimension datums N and P using the 2x hole callout and positioning them relative to each other with the 4,000ths position tolerance and the perpendicularity applied individually. Okay, so this is all referencing drawing GDTG 00401, which I discussed extensively in that video, episode 6 on dowel pins, and which was posted on May 26, 2023. So here's that 2x callout for the dowel pins. Not actually a hole callout, okay? And the 4,000ths diameter position tolerance that ties them together as a pair. And then below that is the perpendicularity applied individually to each dowel pin. I specify this dowel pin as being datum feature N and this one as being datum feature P. Okay, so now back to the comment. And then you use the translating datum modifier on the tertiary datum in the feature control frames of the features controlled relative to the pins. Yeah, exactly. So in the callout for the threaded holes, I referenced datum P as tertiary with the translating datum modifier. And same thing for this all-around profile control. So then our commenter continues, what does the translation modifier get us in this instance? It seems like it communicates which of the pins engages with the slot, but it doesn't seem like it gives any bonus tolerance or affect the origin of the datum reference frame. All right, let's first talk about bonus tolerance. Bonus tolerance is a great concept, but when you see these material modifiers like this circle M in the datum references, that is not really anything to do with bonus tolerance. Circle M over on this side, in the tolerance, that can denote bonus tolerance. Now, as an aside, there's not much bonus tolerance here for a threaded hole, but there could be meaningful bonus tolerance on a screw clearance hole in the mating part, for instance. The material modifiers in the datum references are much more about how the datum feature is going to behave in assembly, how it is going to interact with the locating features in the next part. And so, yes, we put the translating datum modifier on the datum P pin because it is the feature that is going to interact with the slot in the next part. The pin that locates into this hole here is going to interact around the entire circumference, whereas the pin that locates into the slot is only going to have a couple of contacts on the sides. Remember, the reason we do the slot is because we want to avoid a condition of over-constraint and still have excellent repeatability. If we had two very close-fitting holes here, we would have to very closely control the distance between the two holes and the distance between the two pins. Otherwise, the parts would not fit together because of over-constraint, or we would have to have bigger, looser-fitting holes, which would cost us our repeatability. Okay, so it's a little funny that we put the translating datum modifier on the drawing for this part with the pins. because the datum P pin doesn't move. It's stuck firmly in the machined aluminum piece. But it's not really the pin that translates. It's the datum simulator that translates. For instance, we have these circle M maximum material boundary or MMB modifiers. What these tell us is that these datums can be simulated at the maximum material boundary of the feature. So let's make a note of that. The modifiers tell us about the datum simulators. Now my drawing GD&T 00401 showed what I call a detail area of a larger part. But now I think it would be helpful to get away from that and to show the larger part. So here's an idea for what it could be. A bigger plate where here you see the interface we have been talking about. All right, and here's a drawing I made, GD&T 00459, where I'm trying to recreate the approach that our commenter describes. And I just want to point out one thing quickly here on sheet 1, flag note 4, because in the Dowel Pin videos and on GD&T 00401, I made a point that I felt like I needed to say that when it comes to the pressed-in pins, the tolerances and datum references apply only to the protruding portions of the pins and not to the portions that are pressed down into the aluminum. But I had some colleagues point me to paragraph 7.4.1.3 of the 2009 standard under the section on projected tolerance zone, which says more or less the same thing. So I feel like I can delete this. And we could, and maybe should one day, talk about whether there can be a good reason to spell out some of these more obscure elements of the standard. And we'll probably get into some of that here in this very video. But I lean pretty heavily toward a concern that any of these notes can cause more confusion and misinterpretation, especially if they give the appearance of bending the usual GD&T rules, like this appears to do, even though it does not actually. And this is a tough attitude, but I already say here in the title block that this is a Y14.5-2009 drawing, which kind of puts it on everybody else to learn the standard. Like, someone else's ignorance of the standard is not really my responsibility. Am I supposed to reproduce all the relevant elements of the standard in the general notes of every drawing? Of course not. Am I supposed to pick and choose what I think someone is going to understand or not understand from the standard? I want out of that. Sheet 3 here is where we will really start digging into the dimensioning method our commenter describes. You'll see that the logic of this sheet is that on the left side, we have some orthographic views of the entire part at 1/4 scale. And then on the right side, we have the detail view, similar to what you saw in Dowel Pins video 6. Okay, I said that was sheet 3 because on sheet 2, I would have detailed out the mounting interface of this part and applied tolerances to the datum features A, B, and C, which are the locating features of this part in assembly. But I just haven't done that yet, so I hope you can forgive me. By the time we get to sheet 3, the idea is that datum reference frame A primary, B secondary, C tertiary at MMB is already established. And then here in the detail view, we are talking about datum reference frame M primary, N secondary at MMB, P tertiary at MMB. So how do we get from ABC to MNP? That's in these views on the left. First, let's look at that primary datum feature M. Here in this view, I can see it has a basic dimension off of datum A with positional, orientation, and form control. Now, in this view above it, I have basic dimensions from the B and C datums out to one of the dowel pins, which is, I think, how the commenter described it. All right, and now if we go over to detail view C, we have a position for this first dowel pin within the ABC datum reference frame, as well as a perpendicularity to datum M. Well, to help us think about datum reference frame ABC, let's look at a fixture. You know I love my gauges and fixtures. This one has a datum A simulator, this large surface, a datum B simulator, which would be these two surfaces, and a datum C simulator, which is this key made at 0.496 wide. And I'm asking you to believe that this is all very precisely made, inspection quality, effectively perfect for our purposes. So these datum simulators could be indicated in on a CMM to find the XYZ coordinate system for this datum reference frame. And then manufactured parts could be placed onto this fixture for inspection. And so I guess the first thing you could do here would be to inspect the position of this pin in the ABC datum reference frame. This would allow us to check this positional requirement here on GD&T Guy 00459, 20 thousandths diameter at MMC. Okay, then there are a few other requirements like the perpendicularity of this first pin, the position of this second pin, and this all-around profile, and the position of the threaded hole pattern that we should be able to check with one special gauge. Here we have this 0.2507 diameter hole to fit over the first pin. Because 0.2507 is the MMC size of the dowel pin, 0.2503, plus the 4/10 perpendicularity tolerance. So if the gauge fits over this pin and makes solid contact with the datum M feature, we can say we pass this perpendicularity requirement. Okay, and so back to the gauge. To fit over the second pin, we have this 0.2583 hole. I get 0.2583 by adding the pin MMC size, which is 0.2503, plus the 8 thousandths position tolerance. So the gauge will verify the position tolerance on this second dowel pin, but it doesn't really say anything yet about the perpendicularity of the second pin. The gauge can now be used as a simulator of the MNP datum reference frame. You can see it is pocketed here to act as a sort of go gauge over the all-around profile, and it has these 270 diameter holes, which are the virtual conditions for the thread locators. Stuff we saw in the old video about GD&T Guy 00401. When we place this onto the inspection part, we can use it to verify the all-around profile and the threaded hole positions. All right, so what's not to like about this? Well, it's a little strange that in the gauge, the one datum simulator hole is a little larger than the other one, which means that it's free to wiggle a little bit. And that's just because we're really not able to take advantage of this perpendicularity on the second pin. If you go and read this paragraph 4.11.6.1 and the accompanying illustration on figure 4-16, and if you think about it for a minute, you'll see that the MMB of datum feature P here has to be calculated as MMC size plus position tolerance. If I went into my gauge and made both holes 0.2507 diameter, we would not be allowing for this 8 thousandths of position tolerance, and the gauge wouldn't fit over many good parts. You get that? And so there is very little reason why to even put in a perpendicularity requirement on the second pin, and it could easily be left out. Now, there is actually a bigger problem here, and it is the reason I call this drawing insufficiently defined. And that is that we have never said where this second dowel pin is located in datum reference frame ABC. We locate the first pin, and we give the distance between the two pins, but we don't have anything that controls the orientation of the pattern of the pins. Which is really unfortunate because it's probably a major reason we are using this pinned interface to control this orientation very closely. My guess is this would be a bad part. But of course, if we were to do our inspections on this bad part, it would still pass, wouldn't it? I can hear the howls of protest now. That wouldn't happen. Everybody knows my intent is that the pattern would have good orientation control, and so on. Save it for someone who doesn't go on the internet calling himself the GD&T guy. It's underdefined. Go read in the standard, the fundamental rules A through D. This is section 1.4. We can't leave this pattern of features free to swivel around on the basic location of the first pin. We need dimensions that will define its basic orientation, and there needs to be a tolerance, some kind of tolerance, so we know what's acceptable and what's not. And another note, don't be thinking that you can just sprinkle a little magic datum B reference into this callout right here. That would put you in the area of the bogus datum reference frame if you saw my video on that topic. You do need to bring datum B into it, but there are better ways of doing that. So this is why I recommend an approach like I have here on GD&T 00460, and this is sheet 3. Here I give basic dimensions for both dowel pins in the interface from datum reference frame ABC. Now look, these pin locations trace back to some reference geometry in the CAD model. See how everything is at this 30 degrees or its complement 60 degrees? I think it could be possible to replicate that in this drawing view here with some center lines, basic angle, basic dimensions pointing to the intersection of the lines, etc. But if we think about this part being set up on the CMM with the datum simulators indicated in and a 000 on the intersection of the 3 datums ABC, at least in this case, I like to give the inspector what's effectively the coordinates of these pin locations in that datum reference frame ABC. And I generally like my drawing dimensions to be exactly what's in the CAD model. And so I went out to 4 decimal places. And I like how with this, I'm not placing a trigonometry problem on anyone. That said, it could be interesting for a drawing like this to have a view with a reference dimension for that angle on the center line maybe of these 2 dowel pins going back to datum B. Total side note here, but I've always liked how something special happens at 60 degrees, where you get these super clean XY positions. Anyway, I locate these 2 pins with basic dimensions, and then in this callout up here, I have 2x dowel pins, and I'm talking about them as a pattern of features. This is a lot of the same approach that I used in that episode 6 video of dowel pins as locating features. Now you'll see that we have this huge heap of feature control frames, but don't sweat it. There's only one thing that's new here. Just like we had before, we still have the 20 thousandths diameter position tolerance referencing datum reference frame ABC. But how about this? Composite position with the bottom frame, the FRTZF referencing A primary, B secondary. So the pins are located to the 20 thousandths by the upper frame, the PLTZF, but then within that, the pattern is controlled in orientation to a tighter 10 thousandths in the FRTZF. That seems like a great thing for this part. Everything about this design communicates to me that the orientation of whatever goes on these pins is an important design consideration. And probably also what one commenter to the dowel pin videos called the insertion accuracy of whatever goes on these dowel pins. I'm glad to have that in my lexicon. Okay, so the composite position is a great way to refine the positional requirements of these pins within ABC. Then there's nothing new. I locate them together as a pattern now with the 4 thousandths. Okay, so that's 2 cylinder-shaped tolerance zones, 4 thousandths in diameter, located on their basic positions. This is analogous to plus or minus 4 thousandths pin to pin. And then, of course, perpendicularity, which I say applies to the individual pins, not the pattern in this case. Okay, and here I told you that it was a good idea to have that perpendicularity because now, with translating datum modifier in all my datum P tertiary references, we could start using a gauge that has a translating datum P simulator, in this case, sliding within a groove. And because of that, we can start calculating maximum material boundary as the MMC size plus perpendicularity tolerance to get us to a place where both of these holes are the same size now, 0.2507 diameter. Sounds good, right? Okay, well, listen to this. Over a year ago now, and I've been sitting on this for far too long, 2 colleagues told me that they had seen my video And I was wrong. They showed me the chart on figure 4-16, and they showed me 4.11.6.1, which say that it has to be MMC size plus position, not perpendicularity. And I say, okay, but that's not taking into account translating datum modifier, the ability for the gauge feature to slide. To which one of these guys said, well, where does it say that? And so I began to search. And my friends, I am still searching. But I am becoming convinced that what I am looking for is not there. I think it's not in 2018 either. Nowhere, apparently, does it say that translating datum modifier switches us to using perpendicularity to calculate MMB. But I'm like, what is even the point of translating datum modifier if you can't use perpendicularity to calculate MMB? This is not how you want to start a conversation at a party, by the way. But look, this is the same reason we use a slot in the part that locates onto these pins. We can make that slot a close fit on the pin, improving the repeatability of the assembly. Okay, so unless I'm totally missing something, this is crazy cuckoo bananas, because now I'm thinking that I have to do some unusual stuff to fix the situation. One idea is to write a new general note. So here's what I got here in GD&T 00460. For any external cylinder, including dowel pins, given a perpendicularity tolerance in addition to any position tolerance, referenced as a tertiary datum feature at MMB, and with a translating datum modifier applied, the MMB can be calculated as the MMC size plus the perpendicularity tolerance, overriding ASME Y14.5 2009, paragraph 4.11.6.1c. Don't you just love the English language? This is poetry. But I don't know if anybody else is going to appreciate this as much as I do. Having it on the drawing is going to cause people to panic, I worry. I think this should just be in the standard. I don't want this on the drawing, but because it's correct, I think it's okay as a workaround solution to this problem. So that's on GD&T 00460. But what are some other tools that we can work with? So this is GD&T 00461, and we are here on sheet 3, where everything is pretty similar except for the callouts for the profile and the threaded hole position. The standard says that we can actually use any boundary size that we like if we put it in brackets like I have here in these datum P references. So again, for this one, I feel like it's correct and that maybe, just maybe, there's something more elegant about this than the long general note. But I'm still a little worried that this is going to be the cause of a lot of head scratching in machine shops. Even though in reality, it's still, I think, a totally reasonable thing that anybody who does this work can understand if it's explained to them. But I think this should just be changed in the standard so that if you have the translating datum modifier, you can just say circle M and you get the 0.2507 diameter. Then, my dear friends, after stewing in this for literally months, the marble in my head rolled into a different hole, so to speak. If I can enter in any value for the boundary size of a datum feature, what's the best application for that? Well, my efforts here recently have been to get the datum P simulator down to the same size as the datum N simulator, 0.2507 diameter. But I've been thinking, whoa, that's a close fit over a pin that can be 0.2503 and has only a very small amount of perpendicularity tolerance. It seems like this gauge would be difficult to get onto the pins, even on a good part, and it would probably wear out quickly. Let's have a little review of the drawing for the part that locates onto the pins, GD&T 00402. You'll see that the pinhole and the slot have the 0 perpendicularity tolerance at MMC, and that the MMC is 251, so the virtual condition is 251. I'm thinking if 251 is good enough for our part, it seems like it should be good enough for our gauge as well. So here on drawing GD&T-G00462, I have that value written in as the boundary size for the datum simulators for both P and for N. To me, it seems like I have done a pretty nice thing here for the toolmaker and for any inspector who uses a gauge like this, if one is ever made. But I gotta tell you, I'm torn because part of me knows that there's probably gonna be meetings called to discuss whether I should be shot in the street for submitting something like this. But at the same time, it's good GD&T. So what are you gonna do? Well, for now, let's bring this around full circle to where we started. Just to repeat from the comment, what does the translation modifier get us in this instance? It seems like it communicates which of the pins engages with the slot. Yes. But it doesn't seem like it gives any bonus tolerance or affect the origin of the datum reference frame. Yeah, I would think not. It's not really about bonus tolerance. Does the presence of the modifier affect if this part will be rejected or accepted if it were measured with a CMM? Well, listen, I've never operated a CMM. The term CMM is not used in the standard either. All of these times that I'm talking about gauges, I'm really talking about true geometric counterpart and datum simulators. The standard deals in the language of true geometric counterpart and datum simulators. So I would think that anything you do on a CMM, even if it creates complexity, would have to be aligned with that way of thinking. But I'll tell you what, if you don't use translating datum modifier on the tertiary, yes, your parts are more likely to pass inspection. But that's just because the MMB size of the tertiary datum simulator will be big. MMC plus position tolerance. I guess it's a little like bonus tolerance because your gauge will be able to rotate around on that first pin a little bit to try to pick up the threaded holes with the locators. But if your mating part has a close-fitting slot, you don't actually have that quasi-bonus tolerance, do you? You don't have much wiggle in your assembly. You need the datum simulator to be MMC size plus perpendicularity, and you also need for it to be able to translate so it's not over-constrained. Okay, super full circle now. I told you in the very beginning of the dowel pin videos, this interface with the hole in the slot over 2 pins is common to the point of ubiquitousness, and for good reason, because it is also useful and elegant. But for all of that, it makes for some challenging, as you can see, non-entry-level GD&T, which, as it happens, is a lot of what we do here on GD&T Guy. Let me know what you think in the comments.